Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
So, I was actually walking through the Museum of Modern Art a few months ago.
Oh, nice.
Yeah, trying to get some culture, you know how it is.
Mm-hmm.
And I found myself just kind of standing in front of that small, almost unassuming canvas by Salvador Dali.
The persistence of memory?
Exactly. The melting clocks.
Right.
You know, the pocket watches draped over dead tree branches and sliding off tables looking like, I don't know, slices of cheese left out in the sun.
It is a very striking visual.
It really is. And usually when you look at that painting, you think about the psychology of time. You think about how an hour in a dentist's chair feels like a week.
Oh, yeah, absolutely.
And an hour with a good friend feels like a minute.
Hmm.
We tend to think of memory and time as these purely internal, fluid experiences.
Completely subjective.
Right, completely subjective.
Okay.
But standing there looking at those warped watches, I started wondering if Dali was accidentally stumbling onto a literal truth about physics.
That is a fascinating leap.
Because we tend to think of the physical universe, you know, the hard vacuum of space, as this rigid container. A clock is a clock. A meter is a meter.
The stage where things happen.
Exactly, the stage. But what if the container itself? What if the stage actually melts? What if the universe has a memory and that memory looks like a permanent physical distortion?
That is honestly the perfect mental anchor for what we are unpacking today.
I thought it fit pretty well.
It does, because in the world of general relativity, specifically in the study of gravitational waves, there is a phenomenon literally called memory.
Capital M, memory.
Capital M, and it suggests exactly what you just said. It suggests the universe isn't just a static stage that events happen on. It suggests the stage itself is recording the play.
And just so you listening are clear, we aren't talking about metaphor here.
No, not at all.
We aren't talking about history in the sense of writing it down in a physics textbook. We are talking about the actual fabric of space-time getting bent by a catastrophic event, and then, and this is the crazy part, never bending back.
That is the core concept. It is a permanent scar on the geometry of reality.
A permanent scar. So for this deep dive, we are looking at a brand new study. This is published in Physical Review Letters in February 2026.
Fresh off the presses.
Right. It's titled The Persistence of Gravitational Wave Memory. And it's led by Antonio Sakaros and his team.
Who are out of the University of Illinois at Urbana-Champaign and the Academy of Athens, I believe.
Yeah, along with collaborators from the University of Valencia and Montclair State. And they've basically been simulating what happens when two of the most violent objects in the cosmos slam into each other.
Binary neutron stars.
Right. And our mission today for this deep dive is to really understand how the universe records its own history.
It is quite the mission.
It is. We need to figure out why neutron stars are so much more complicated than black holes, what role ghost particles like neutrinos play in all this, and ultimately why this new study is considered such a massive stress test for Einstein's theory.
It is the ultimate stress test. But it takes something we thought we understood, gravitational waves, and adds a layer of messiness that is, frankly, terrifying to simulate.
The mess. We love the mess. But before we get to the messy stress test, let's set the baseline.
Good idea.
Because we need to understand the difference between a ripple and a scar. Most people listening have probably heard of gravitational waves by now. LIGO detected them back in 2015.
Nobel Prizes were handed out?
Exactly. We know that when big things crash, space ripples. But to understand the new stuff, we need to know what exactly we are crashing together in this specific study.
Right, so we are looking at binary neutron stars, two neutron stars orbiting each other.
Give me the physical reality check here, because I know they are dense, but help me visualize what we are actually dealing with.
Sure. So imagine a star that started out much, much larger than our own sun.
Yeah.
It burns through all its nuclear fuel over millions of years, and then the core collapses. It goes supernova.
The big boom.
The biggest. The outer layers blow off into space, but the core itself gets crushed inwards by its own gravity. It is squeezing so hard that the electrons and protons inside the atoms are literally forced together to become neutrons.
So it's basically just a city-sized atomic nucleus.
That's the classic analogy, and it holds up perfectly. You have a perfect sphere, maybe 12 to 15 miles across.
So like the size of Manhattan.
Or London, yeah. but it contains up to 2 times the mass of our entire sun.
That density is it's hard to even wrap your head around.
It is. Try this. If you took a teaspoon of neutron star material, literally just a sugar cube's worth, it would weigh about 1 billion tons.
1 billion tons.
Yeah.
In a teaspoon.
That's roughly the weight of Mount Everest compressed into a spoon.
Okay, wow. So we are taking 2 of these Everest spoon stars, spinning them around each other at a fraction of the speed of light, and just smashing them together.
Exactly. And as they spiral in towards each other, they churn up the fabric of space-time. They create gravitational waves.
Now, the standard explanation, the one I always see in headlines, is the ripple in the pond analogy.
Right, the classic.
You throw a rock into the water, and ripples move outwards. If I'm a rubber duck floating on that pond, I just bob up and down as the ripple goes by.
Right. And in this analogy, the rubber duck represents a detector here on Earth, like Lego, or maybe 2 astronauts floating in space.
Okay.
As the gravitational wave passes through them, the actual space between them stretches and squeezes. They get closer, then further, then closer, then further.
Bobbing.
Exactly. That is the oscillatory part of the wave, the back and forth.
And this is the key thing I want to focus on. Once the wave passes, the pond goes flat again. The rubber duck ends up exactly where it started. The astronauts return to their original distance.
That is what happens with a standard wave, yes.
Mm-hmm.
It's temporary. The universe is assumed to be elastic. It snaps back.
But the memory effect that this paper's about says that's wrong.
It says it's mostly right, but not entirely right. General relativity actually predicts that in addition to that back and forth oscillation, there is a DC component.
DC, like direct current.
Yes, a direct current, a permanent offset.
So to go back to the astronauts in space.
The wave passes, they bob back and forth, but when the wave is completely gone and space is quiet again, they look at each other and realize they are now slightly further apart or slightly closer together than they were before the wave hit.
And they stay that way forever.
They do not snap back. The ruler itself has been lengthened or shortened. Space-time has been permanently displaced.
That is haunting. I mean, it implies that every single time 2 black holes or neutron stars merge anywhere in the universe, the geometry of the entire cosmos gets shifted a tiny bit.
It does. It's a very, very small shift.
Yeah.
Usually undetected by our current instruments because it's so subtle, but mathematically it has to be there. The universe literally remembers the event by changing its shape.
Okay, so that's the what. It's a permanent scar on reality. But I really want to get into the why. Because looking at the history of this theory and the sources, it seems like physicists have been arguing about this for like 50 years.
Oh, easily. It's definitely not a new idea, even if these specific supercomputer simulations are new. The foundation goes all the way back to the 1970s.
1974, right?
Yeah.
With Zeldovich and Polnareff.
Yes. Yakov Zeldovich and Alexander Polnareff, 2 brilliant Soviet physicists. They were working with what we call linearized gravity.
Linearized gravity, which is basically the light version of Einstein's equations.
Exactly the light version, the simpler approximation. And even in that light version, they realized that if you have a system of stars that permanently changes its arrangement, say a cluster of superdense stars suddenly flying apart, the gravitational field at a great distance creates this permanent shift.
It was just a theoretical prediction at that point.
Purely theoretical. The logic was simple, though. If masses move away to infinity, the metric of space-time has to change.
So that's what we call the linear memory. The stars moved, so the gravity changed. Basic cause and effect.
Right. But then came the 90s. And things got profoundly weird.
Enter Dimitrios Christodoulou.
Yes, in 1991, he published a paper that is still considered a massive landmark in the field. He didn't use the light version. He looked at the full, unadulterated, nonlinear Einstein equations.
I actually want to pause on that word, nonlinear. We hear it all the time, right? Nonlinear dynamics, nonlinear storytelling. In this context, does it just mean complicated?
It means that the output of a system literally becomes an input for the system.
Okay, give me an example.
In a linear system, you have a choir singing. That's the source. And the sound waves are the output. The sound waves travel through the air to your ear. They don't really interact with each other.
Right. If the choir sings louder, the sound is just louder. It's a straight line from cause to effect.
Exactly. But in a nonlinear system, imagine the choir sings so incredibly loud that the sound waves actually compress the air enough to heat it up. That heat changes the density of the air in the room, which then changes how the sound travels, which might create entirely new sound frequencies. The sound itself is changing the medium it travels through.
The output messes with the input. So apply that to gravity.
Well, Einstein's great insight was that mass equals energy, E equals mc squared.
Right.
You have mass, you have gravity. But if you have energy, you also have gravity.
And gravitational wave, they carry energy.
Exactly. We know they carry energy because we can detect them. They physically move the heavy mirrors in the LIGO detectors. That takes actual work. It takes energy.
Sure.
So Christodoulou realized if gravitational waves carry energy, then gravitational waves must have their own gravitational field.
Wait, the gravity has gravity.
The gravity has gravity.
That sounds like a recursive loop that would just immediately crash a computer.
It makes the math incredibly difficult, which is exactly why it took from 1974 until 1991 to mathematically prove it. Christodoulou showed that as these waves ripple out from a collision, the massive energy in the waves themselves creates a secondary gravitational distortion.
So it's not just the physical stars smashing together that creates the memory scar. It's the waves themselves piling up as they travel.
Yes. This is called the nonlinear memory, or the Christodoulou memory. The waves effectively gravitate. They pull on space-time as they travel through it, and this effect accumulates. It builds up over the entire duration of the wave signal.
So we have the linear memory, which is just the stars moved, and the nonlinear memory, which is the energy of the scream scarred the air.
That is a fantastic way to put it. The energy of the scream scarred the air, and for a long time that combined picture was all we had, and we modeled this mostly using black holes.
Because black holes are clean.
They are the simplest macroscopic objects in the universe. A black hole has mass, it has spin, and it can have an electric charge. That's it. No surface, no atmosphere, no chemistry, just pure curved space-time.
Right.
So when you program a computer to simulate two black holes merging, you don't have to worry about fluid dynamics or magnetic fields or particle physics. It's pure gravity.
But the universe isn't always clean. And that brings us to the actual meat of the new study by Sakharos and his team. They didn't want the clean version. They wanted the full, messy reality of neutron stars.
And neutron stars are distinct because they are actual physical objects made of ultra-dense matter. They bring extra ingredients to the party, they have magnetic fields, they emit light, and crucially, they emit neutrinos.
And so Sakharos has essentially asked, do these extra ingredients actually contribute to the permanent space-time scar?
Yes.
Which is a really fair question.
Yeah.
Because if energy equals gravity, and neutrinos carry energy, and magnetic fields hold energy, shouldn't they leave a mark too?
Exactly. And to be fair, previous researchers had laid the groundwork for this. People like Lydia Bieri, Poning Chen, Xingtong Yao, and Dave Garfinkel. They had done the pen and paper math to prove that, theoretically, electromagnetic fields and neutrinos should contribute to the memory.
I saw in the sources this is sometimes called null memory. Why null?
Oh, it relates to radiation traveling along what physicists call null infinity, which is basically the mathematical boundary or path that light rays and massless particles take to get infinitely far away from a source.
Null infinity. As to say, physics has the best names. It sounds like an indie rock band.
It really does. But the point is, while the theory for null memory was there, no one had successfully run a full-scale numerical relativity simulation of a binary neutron star merger that actually quantified this.
No one if we put numbers to it.
Right. No one had tracked the neutrinos and the complex magnetic fields and said, okay, here is exactly how much of the memory they create.
Until now. So let's get into the simulation. They built a digital universe. They put two massive neutron stars in it. They gave them realistic magnetic fields and neutrino emissions. What did they find?
They found that the mess matters a lot.
Put a number on it for me.
The simulations suggest that the contributions from the extra ingredients, the magnetic fields, the neutrinos, and the baryonic ejecta, which is the physical matter thrown out of the crash account, for anywhere from 15% to 50% of the total gravitational wave memory.
50%. Up to half of the scar on the universe is caused by the extras.
Yes. If you were to simulate this event and just treat the neutron stars like black holes light, completely ignoring the neutrinos and the matter, you could be wrong by a factor of 2. You'd be missing half the story.
That completely changes the picture. It means you absolutely cannot just look at the gravity of the masses. You have to look at the particle physics.
It forces a total marriage between gravity and nuclear physics.
Take the neutrinos, for example. I usually think of them as these ghostly little things that don't interact with anything. Like there are millions passing through my thumb right now.
Trillions, actually.
Trillions. And normally they are totally gravitationally insignificant.
Right. But a neutron star merger is not a normal environment. When these stars crash together, the temperature spikes to billions of degrees. The nuclear matter is literally being crushed and boiled at the same time.
What does that do?
It releases a flood of neutrinos that is frankly hard to comprehend. The paper mentions a total energy release of around 10 to the 53 ergs.
Yeah, I saw that. And I know ergs is a unit of energy, but I have zero intuition for that. Is 10 to the 53 a lot?
It's an astronomical number. For context, our sun, over its entire 10 billion year lifespan, will emit something like 10 to the 51 ergs of energy.
Wait, so this single crash releases 100 times more energy in just a few seconds, just in neutrinos, than the sun does in its entire 10 billion year life.
Exactly. It is a sudden explosion of energy that briefly outshines the entire galaxy in neutrino radiation. And because E equals mc squared, that massive energy has a mass equivalence.
So as these trillions of neutrinos stream out of the crash site in all directions, they're effectively carrying an immense amount of mass away with them.
Right. Imagine the crash site is losing weight incredibly rapidly. That sudden change in the mass distribution, that lightening of the central load, causes a massive shift in the gravitational field. That is the neutrino memory.
It's like if you were standing on a trampoline holding a heavy bowling ball. The trampoline is curved down around you. If you suddenly throw the bowling ball away, the trampoline snaps to a new, shallower shape.
That's a very good analogy for the linear part of it. The mass has moved, so the curve changes, but there's also the nonlinear part we talked about. The neutrinos themselves are dragging space-time as they fly outward, and the study showed this combined effect is a huge component of the final memory signal.
And there's a specific visualization in the paper they mentioned that really caught my eye. A blue rectangle. Can you describe what we're looking at there?
Sure. So this is a graph showing the strain, basically the memory accumulation over time. On the horizontal axis, you have time in milliseconds. On the vertical axis, you have the memory building up.
And what exactly does the blue rectangle highlight?
It highlights the time duration over which 90% of the post-merger memory is accumulated. For a black hole merger, the memory happens in a literal snap. It's a step function on a graph. Nothing, SNAP, full memory.
Instant scarring.
But for neutron stars, the blue rectangle shows that the memory builds up gradually. It takes tens of milliseconds, which sounds fast, but is an absolute eternity in this specific physics context, for the memory to reach its full height.
Why the delay? Why doesn't it just snap like a black hole?
Because the neutrinos take time to leak out of the ultra-dense core. The ejected matter, these massive clouds of gold and platinum dust, takes time to expand outward. And the remnant itself, the hypermassive blob of matter left over from the crash, wobbles and sloshes around for a while before finally settling down.
So it's a slow-motion scar.
Exactly. And that slope, how fast or slow the memory builds up, tells you immense amounts about the internal physics of the explosion.
Now, speaking of the internal physics, we have to talk about the magnetic fields. Because this is where my own naive assumption totally failed me while I was reading.
What was your assumption?
Okay, so my logic was pretty straightforward. I know these stars are giant magnets. Magnetars are some of the scariest things in space. And I know energy equals gravity. Magnetic fields contain energy.
Solid logic so far.
Right, so if I take two stars with super strong magnetic fields and smash them together, I'm adding more energy to the whole system than if they were unmagnetized. More energy should mean more gravity, which should mean a much bigger memory scar.
That is entirely logical. It is what we call the naive expectation. And I don't mean that as an insult at all. It's exactly what many physicists expected too before they ran the numbers.
But the simulation said no.
The simulation showed that in some cases, adding incredibly strong magnetic fields actually reduced the final gravitational wave memory.
How was that possible? Where did all that magnetic energy go?
The energy is absolutely there, but it's not making gravitational waves. You have to remember a key rule. Gravitational waves are generated by asymmetry.
Asymmetry.
Yes. They are generated by what we call the quadrupole moment. Basically, you need a lumpy, uneven, wobbling distribution of mass to shake spacetime.
A perfect sphere doesn't make waves.
Correct. Even if a perfect sphere is spinning incredibly fast, it is symmetric. No waves are produced. You need the wobble.
Okay.
Now think about what a strong magnetic field does to a ball of highly conducting fluid, which is essentially what a hot neutron star is.
It holds it together.
It creates magnetic viscosity. It creates tension. Imagine stirring a cup of water with a spoon. It splashes everywhere. It swirls. It's highly turbulent and chaotic.
Right.
Now imagine stirring a cup of cold honey or molasses.
It moves way slower. It's stiff.
Exactly. The strong magnetic field acts like a stiffener. It links the fluid elements inside the star together. When the stars crash, if the magnetic field is strong enough and shaped a certain way, it actually suppresses the fluid turbulence. It prevents the massive sloshing and forces the resulting merged blob into a more symmetric, stable shape much faster.
So the magnetic field acts like a straitjacket for the star. It stops the blob from sloshing around as much.
And less sloshing means less asymmetry. Less asymmetry means less gravitational radiation. So even though you have physically more energy stored in the magnetic field itself, you have less dynamic shaking to create the memory signal.
That is wildly counterintuitive. It's like saying that crashing a sports car at high speed might actually do less structural damage to the environment if the car is made of a much stiffer material.
In a way, yes. The internal dynamics matter more than the raw energy count alone. And the study found this memory dampening depends heavily on the topology of the field.
Topology. That just means the shape of the magnetic field, right?
Yes. Is the magnetic field aligned perfectly with the star's spin? Is it tilted perpendicular? Is it a toroidal field, meaning it's shaped like a donut entirely inside the star? The study showed an intricate dependence on these shapes.
Meaning you can't just guess the outcome based on energy.
You absolutely cannot guess. You have to run the supercomputer code for every specific scenario.
This brings us to the real face. So what are the episode? We've got these amazing simulations. We know that neutrinos and magnets and gold dust all contribute up to half of this scar in the universe. But we haven't actually seen this yet, have we? LIGO hasn't flashed a red light saying memory detected.
Not yet, no. We have successfully detected the oscillatory waves, the chirp of the merger as they spiral in. But the memory is a very low-frequency effect. It's a permanent DC offset.
And current detectors just can't see that.
Current ground-based detectors like LIGO are not great at seeing things that happen slowly or just stay put.
Why is that? Because of the Earth.
Exactly. Think about how LIGO actually works. It's a series of heavy mirrors hanging on delicate glass threads. It's looking for high-frequency vibrations. If the mirror moves and then just stays moved, it's incredibly hard for the computer to tell if that was a permanent gravitational wave memory, or if the tectonic plate under the building just shifted slightly, or if a truck drove by, or even if the laser slightly heated up the mirror.
The permanent shift just gets lost in the everyday noise of the planet.
It just looks like instrument drift. But with next-generation detectors, like the Einstein telescope, which they are planning to build deep underground in Europe, or LISA, which will be a triangle of satellites flying millions of miles apart in space, we should finally be able to separate this subtle memory signal from the noise.
And when we do find it, what does it actually tell us? Why are so many physicists dedicating their careers to hunting for this scar?
Because it is the ultimate forensic tool. If we can cleanly read the memory signal, we can essentially reverse engineer the dead star.
This connects back to a term I saw all over the sources: equation of state. I really want to drill down on this. What exactly is an equation of state?
In physics, an equation of state is simply a mathematical rule that connects density to pressure. For the air in your car tire, it's simple physics. You compress it, the pressure goes up linearly. But for the exotic matter inside a neutron star, we genuinely don't know the rule.
Because we can't build a neutron star in a lab on Earth to test it.
Right. We cannot squeeze normal matter to nuclear densities on Earth without it just becoming a bomb. So we don't know what happens at the very core. Is the core squishy? Is it extremely stiff? Is it made of regular free neutrons? Or does it melt down into a bizarre soup of free quarks? We just don't know.
And whether it's stiff or squishy changes how it crashes.
Drastically. A stiff star strongly resists collapsing. It bounces. A soft, squishy star smushes together very easily. That physical difference changes how the whole merger happens, which changes the shape of the gravitational waves, which ultimately changes the slope and size of the permanent memory scar.
So if we detect the memory scar with LISA, we can look at its precise shape and say, aha, that scar means the star was squishy. Therefore, the core couldn't have been pure quark matter.
Precisely. The space-time memory inherently encodes the hidden nuclear physics of the core. It's a way to look deep inside an object that we can never, ever visit.
And beyond the forensics of the star itself, it's also a massive test for the fundamental theory of gravity.
It is the stress test we mentioned at the start. General relativity is over 100 years old now. It has famously passed every single test we've thrown at it.
Every single one.
But the memory effect relies heavily on that nonlinearity we discussed. The wild idea that gravity creates its own gravity.
So if we build LISA, and we look for the memory exactly where the simulations say it should be, and it's just not there,
then Einstein was wrong. Or at the very least, his theory breaks down at these extreme high energies.
that would be the biggest news in physics in a century.
It really would. Or, more likely, maybe we find the memory, but it looks totally different than Sakharov's simulations predict. That would tell us we don't understand neutrinos nearly as well as we thought, or that matter behaves in some entirely new way when extreme magnetic fields are involved.
It's a win-win for science. Either we definitively confirm the wildest prediction of the theory, or we break the theory and find new physics.
That's the beauty of experimental astrophysics.
I want to zoom out a bit as we wrap up here. We've been talking heavily about the math and neutrinos and fluid dynamics, but I keep coming back to that Dali painting in the museum. And there was a specific quote from Sakharov in the press release that really struck me.
Ah, the one about the world line.
Yeah. He said, "Similarly to our own persistent memory, which is shaped by the world line of our lives, binary compact objects also develop a persistent memory as described by Einstein's theory of gravity."
It's a beautifully poetic connection for a physicist to make. In relativity, a world line is just your path through four-dimensional spacetime. From the moment of your birth to your death, you trace a unique line.
And he's essentially saying that just like our lives leave physical memories in the neurons of our brains, the violent lives of these stars leave actual physical memories in the fabric of the universe itself.
It implies that the deep history of the cosmos isn't just gone, it's physically recorded. The geometry of the universe right now, today, is the cumulative sum of all the massive collisions and mergers that have ever happened since the Big Bang.
Which leads to a sort of terrifying thought for me. If these mergers have been happening for billions of years across the whole universe, billions of black holes, billions of neutron stars, and each single one stretches space a tiny little bit and leaves a permanent scar.
You're wondering if the universe is getting wrinkly.
I am. Is the universe smoother in the distant past and more distorted now? Or are we essentially accumulating cosmic trauma?
In a very real mathematical sense, yes. The texture of the gravitational field is getting richer, more complex. It's constantly being worked over by these extreme events. We are living in a universe that is physically, geometrically different than it was yesterday, precisely because of the events that happened today.
We aren't just actors on a stage. We're on a stage that is constantly warping and stretching beneath our feet.
And thanks to studies like this one, we are just now learning how to read those warps.
So what's next for the team? They've proved the concept with this simulation.
Sakharov's calls this a first foray. Now comes the real computational grind. They need to run hundreds, maybe thousands of these simulations.
Tweaking all the variables.
Right. Different masses, different magnetic field shapes, different equations of state for the core.
They basically need to build a library.
Exactly. A comprehensive catalog. So when LISA, or the Einstein telescope, finally turns on and catches a memory signal, the scientists can look it up in the library and say, oh, that matches simulation 400 exactly. It was a 1.4 solar mass binary with a stiff core and a toroidal magnetic field.
Decoding the universe's scars.
Multi-messenger astronomy at its absolute finest.
Well, my brain is suitably stretched for one day. We went from melting clocks in New York to the density of Mount Everest in Atiscone to the mind-bending idea that gravity itself has weight.
Just another day in astrophysics.
To recap for everyone listening out there, so you have this locked in. 1. Space-time isn't rigid. It has a memory. Big crashes leave permanent physical scars on the geometry of the universe.
Spot on.
2. Neutron star mergers are incredibly messy. You absolutely cannot ignore the extra ingredients. Neutrinos and ejected matter account for up to half of that memory signal.
The mess matters.
3. Magnetism is weird. It can actually reduce the total memory signal by stiffening the star and making the resulting crash smoother and more symmetrical.
The counterintuitive finding.
And 4. Detecting this memory is how we eventually crack open the neutron star to see what's actually inside the core.
A perfect summary.
I want to leave you with one final provocative thought today. We talked a lot about the universe remembering, about it carrying the physical record of its own violent past. We usually think of the laws of physics as completely timeless, eternal. But if the actual structure of space itself is continuously evolving, if it's constantly accumulating these tiny permanent shifts, these memories,
Right.
does that mean the universe we live in today is fundamentally structurally different from the universe of the Big Bang? Not just because it's older or larger, but because it's scarred. Is the gravity holding you to the ground today exactly the same as gravity yesterday? Or are we all just floating in the microscopic wreckage of a billion cosmic car crashes, finally trying to make sense of the damage?
That is a very heavy thought to end on.
That's exactly why we call it the deep dive. Thanks for listening, everyone.
Keep looking up.
See you next time.